So we spoke quite a lot about directional derivatives on Friday. I did a picture and really tried to explain what they were. There's a formula for working them out. If you're working out the directional derivative of a function in the direction of some unit vector u at some specific point, x0, y0, the formula is this. Please keep quiet. Please keep quiet. There we go. Yeah, and then I did discuss how that h tends to 0 from above you'll find in some resources and you won't find in others, even within old resources from this specific course. So it is a slightly controversial thing. We will be using one-sided limits. Frequently it doesn't matter. Okay, now that's basically determining a directional derivative from first principles. And that is what you need to do if you're not, if there's anything funny going on, if you're not really sure about continuity, you're not really sure about differentiability, if you are 100% convinced that at the point x0, y0, your function is completely differentiable, and it's obvious that it's differentiable because it's just some sort of one of your quadric surfaces or something like that, then there's actually a shortcut. There's a formula that you can use instead of this one. Oops, funniness going on there. If you are 100% certain that f is differentiable, okay, x0, y0, well, I suppose I shouldn't actually say that. I should just say if it is differentiable, but basically I'm giving you, if you approach a problem and you're convinced that the function is differentiable, there is an alternate formula. Sorry, that's written in a rather colloquial and informal way, but I think you know what I mean. duf x0, y0 equals the x derivative at x0, y0 times by a plus the y derivative at x0, y0 times by b, which is, if you've had your coffee this morning, you'll see that that is a dot product. Your green tea, your ginseng, your pronutro, whatever it is, it gives you your sharp intellect at 8 o'clock. And some of you will know, but for some of you it's the first time you're seeing it, that vector that has your two derivatives in it actually has a special name. It's called grad f. So the shortcut formula is to take your grad f and dot it with your AB, and you'll get your directional derivative. What I'm saying here is that the result that you'll get using this formula is the same result that you would get if you used the first principles formula. But if there's any doubt in your mind about whether your function is differentiable, and that usually happens with piecewise defined functions, at the join between the pieces, you can never be quite sure what's happening there. So if there's any doubt about differentiability and you want to work out a directional derivative, you have to use that first principles formula at the top of the screen. Okay. Let me do some examples. Or should I do a proof? Nah, I don't have time, frankly. I'd like to have time, but I don't. So let me do some examples. I'm going to start with 110. Exercise 110. Everybody okay? Questions? No? 110. 110. There we go. Find the directional derivative of this function, e to the x ln y, at some point p21 in the direction of some other point p34, q34. This is quite an unusual problem for this course. One, the function is obviously differentiable, and we usually give you functions that are not obviously differentiable. Secondly, the direction vector is usually given, whereas here you're just given 2 points and you've got to determine the direction vector. I mean, that's hardly a difficult thing to do, but it is slightly unusual. If you read the other problems, they're not usually phrased that way. But I'm just starting off with something that's a little bit easy. So the direction vector, PQ, is, well, let me just, I've mostly been using round brackets, so let me stick with round brackets. 3 minus 2 is 1, 4 minus 1 is 3, there we go. But that is not suitable to be my direction vector that I'm going to use in my calculation, because the direction vector I use in my calculation has to be a unit vector, and that is not. So I'm going to make my unit vector this vector, but divided by its own magnitude to turn it into a unit vector. So let's have a look. That would be 1 plus 9 squared. So it would be 1 over square root 10, 1, 3. There we go. That's my u. Okay. Grad f, which I realize I haven't discussed yet. In fact, tell you what, let me not be silly about this. We haven't, even though I've given you that grad symbol there near the top of the screen, we haven't formally discussed grad, so let me save that for another day. My x derivative is e to the x ln y. My y derivative is e to the x over y. Let me evaluate them at, I'm already writing p. Let me evaluate them at p, which is 2, 1. That's e to the power 2 ln 1. Ln of 1 is 0. My y derivative is e to the 2 over 1. So that's e to the 2. So my directional derivative is going to be the vector 0 e squared dotted with the vector 1 over root 10, 3 over root 10 equals 0 plus 3e squared over root 10. Okay, so there I was using the shortcut formula, if you will, because it's absolutely obvious that function is differentiable. It's an exponential times by log. There's nothing weird going on. There's no possibility of kinks or anything crazy like that. As long as my function is defined at the point, it's continuous and differentiable. It's a perfectly ordinary function. The dangerous bits come in when you're dealing with things that have absolute values. Absolute values, there's always a possibility of a kink. And also piecewise defined functions. Piecewise defined functions, there's always a possibility of a kink, where the pieces either don't join up at all, so the function's not continuous, or even if they do join up, they don't join up smoothly, and hence, even though it's continuous, it's not differentiable. Always that danger. Okay, so that was 110. That was nice and easy. We mostly won't give you easy ones. Here's 111. Sorry about that, but yeah. This course has a certain culture, and yeah, changing culture is hard, as you may have encountered yourself on occasion. 111, consider. Let's have a look. What homework have I given myself? Oh, right, I'm doing 111 and 112, and then you're going to give 113 a go. So 111 looks like this. Now you'll notice in the handbook I've written, it can be shown that f is continuous but is not differentiable at the origin, and then I've written in brackets, can you show this? And then the actual question says, show that all directional derivatives exist. So the purpose of me doing this exercise now is to talk about directional derivatives. But you could get this very same function in a test or an exam, and we could ask you to answer the question, is it continuous? To answer the question, is it differentiable? And then to do something to do with directional derivatives, perhaps. So you need to know how to do those things, and in fact I wouldn't be surprised if that very same function has already been encountered earlier in this handbook. So it's not the purpose of the problem now, but it could be in another context. Okay, directional derivatives. So it says show that all directional derivatives exist. So we're not being asked to find one specific directional derivative. Sometimes we are, like 112b, and if you just scan your eyes down, Yeah, what have we got? 114B, 115F, 116E. So frequently you are asked to find a specific directional derivative. That's not what's going on here. So in this question, I'm going to keep my unit vector generic at AB. I'm not actually going to give my unit vector actual numbers. Right. Let the direction unit vector be this, AB. Okay? I use a little circumflex, a little cuppy for unit vectors. You don't have to, it's not a universal symbol, but that's how I differentiate between any old vector and a unit vector. I use a little cuppy. If differentiability is in doubt, or in this specific problem we're actually told quite explicitly it's not differentiable, we've got to use first principles. So it's f of, so now we follow the formula. So x naught, y naught is 0, 0. Our unit vector we're just leaving out with a, b. So a and b we're not actually giving values to. So it's 0 plus ha, 0 plus hb, minus f of 0, 0 over h. Yeah. Yes. Thank you. Was that a correction of me because I forgot to put the plus in? I swear I did. I'll blame it on the cursor. I did put the plus and the cursor didn't write it. H tends to 0 from above. Okay, so let's have a look. 0 plus HA, 0 plus HB. H is tending to 0, which means by definition H is not 0. So both my x and my y coordinates of that first term there are non-zero. So when I actually put my function in, I'll read it off the top piece of my piecewise defined function. So what have I got? I've got HA, h squared a squared minus h squared b squared over a squared plus, no, yes, ha squared, h squared a squared plus h squared b squared minus, okay, f of 0, 0, well that's just 0, all over h. Sure, that looks big and chunky, but it actually simplifies quite a lot. I am going to take h squared out as a common factor from that little brackety bit at the top there. I'm also going to take h squared out as a common factor from that denominator. And then that h that's at the bottom of the whole big fraction, I'm going to absorb into the denominator of the numerator, if that made sense. So I'm going to have an h cubed altogether. And over here, I'm also going to have an h cubed. Because there's the h squared that I get from the common factor, and it gets that other h from the bottom. Because dividing by h is the same as timesing by 1 over h, so the h comes in. Okay, so the h's cancel, and I'm left with no h's. So h is tending to 0, but who cares? H could tend to anything, there are no h's left. So this is just a squared minus b squared over a squared plus b squared, and there is in fact one further line of simplification that I can put in. What is that extra line of simplification? Anybody? I mean, what I've got there is correct, but it can simplify further. Question, yes? Or answer rather?
You could expand the difference of 2 squares bracket on the top and cancel the 1 bracket on the bottom.
We could do that if the denominator were just a plus b, because then we could do a difference of 2 squares and get a minus b, a plus b, but because it's squares, but I'm glad you're venturing something. Some people are just kind of looking at their friends thinking, I hope you're coming out with an answer, because I'm not. Anything else? It's because we know something about A and B. A and B are not just any old things. They're something special. AB is a unit vector, which means that the modulus of u is 1. Okay? What is the modulus of u in terms of A and B? It's kind of hidden. But that denominator is just 1. Yeah, were you about to offer that? No. Can I help you? Question? No? You're lost in thought? Lost in thought. Right. Because A and B, so we haven't specified A and B, but still they're bound by the fact that they are the components of a unit vector. Which means A squared plus B squared, or strictly speaking, it means the square root of A squared plus B squared is 1. So it follows that A squared plus B squared is 1. So that second last line is perfectly correct. There's nothing wrong with it. But it can be simplified just a little bit by recognizing that the denominator is 1. And, of course, that exists. There's nothing in there that makes it not exist. Give me any unit vector, and I'll just be able to plug in its A and its B, and I'll find the directional derivative. This exists for all AB. There's no way for that to not exist. There's no potential for division by 0 or anything funny like that. Okay, everybody okay? I want to do the next exercise, which is, I'm losing track of my numbers, 112. But I've reached the bottom of my page, so it's going to be an abrupt page jump in a second. Let me just read it. 112 equals, okay, it's another one of those piecewise things. It can be shown that this function is continuous but not differentiable. You need to be able to do that. But we're not going to do it now. Show that all directional derivatives exist. Cool, that's going to be very similar to this. And then the last one, use the directional derivative to find the direction of the tangent line to some curve of intersection. Goodness me, how are we going to do that? So I'm doing a page jump. To begin with, part A is very similar to what we've just done. Let me first write out my function. Okay. Let the direction unit vector be our good friend AB. My directional derivative at 0, 0 will be the limit as h tends to 0 from above of, very similar to the last one. Can you please keep quiet, even if you're talking about maths? Okay, very similar, only this time I'm plugging it into a slightly different formula. So what is it? It's going to be h cubed a squared b over h squared a squared plus b squared minus 0, yes? Mm-hmm.
If let's say x equals 0 or I equals 0, then make it a plane.
So if this piecewise defined function was defined such that instead of just having that f equals 0 at a single point, it was f equals 0 if x or y equals 0, we wouldn't have a plane. We'd basically have two lines, but it's because we'd have z equaling 0 along the y-axis and z equaling 0 along the x-axis and z equaling that thing at the top elsewhere, which wouldn't be so much a plane as two lines in a plane. It wouldn't affect our what we're doing here in our calculation, however, because HA and HB are both non-zero, and hence we would still be plugging it into that funny rational thing rather than into the 0. I don't know whether that addresses your question, because I don't think I was quite answering you there. Okay, you happy? All right, good. All right, we're going to end up with that same deal of the h's all cancelling out. So we're left with a squared b over a squared plus b squared. Yes, there was a question. I'm getting the h cubed, so I'm plugging HA and HB into my function. And so when I square the h, I'll get h squared a squared. And when I put in the y, I'll get hb. So I've got h squared a squared times hb, giving me h cubed a squared b. Then at the bottom, I'll have an h squared from each of the x and the y, and then the h from the big denominator contributes, and eventually all the h's cancel. And once again, there's that little phenomenon of a squared plus b squared. Question? Okay, so in question 110, there was that shortcut formula. And the shortcut formula is you work out your directional derivative using a dot product, where the two vectors that you're dotting are the vector that's made up of your partial derivatives and the unit direction vector. That formula will only give you the correct result if your function is differentiable. It'll give you the wrong result if your function is not differentiable. That formula is only applicable at points where the function is differentiable. And these functions are not differentiable at the origin, and hence, if we use that formula, we'd get the wrong answer. I'm glad you're asking that, because in tests and exams, it's quite common for people to do that. And then they get the wrong answer, and we just have to give them 0 for a question that probably was worth maybe 4 marks. So you don't just lose 1 mark for getting the wrong answer. It's because we have a mark scheme, and there's 1 mark assigned for this and 1 mark assigned for that, etc. And you didn't do any of that stuff, so we can't assign you any marks. So just be careful. Just be careful. The first principles formula will always give you the right result. Always. That little dot product formula will only sometimes give you the correct result, where that sometimes is when the function's differentiable. So if in doubt, use the first principles formula. That's probably a good motto for all of calculus. If in doubt, go to first principles. Right, so that was part A. Oh, I should have one more sentence. This exists. What would it look like to not exist? That would not exist if somehow in the process our h is cancelled. What if they hadn't cancelled and I'd been left with an h at the bottom, and now I'm allowing h to tend to 0? Well, that just blows up. Then it means it doesn't exist for any ab. If my final result here, which is currently a squared b, what if it was a squared over b? That wouldn't exist if b was 0. If b was non-zero, it'd be fine. But if b was 0, it wouldn't be fine. So that's what not existing would look like. Either in the process of solving for the result, it all blows up and nothing exists at all, or you end up with a result that only exists for certain a's and b's, but not for all possible a's and b's. But here, it's fine. Okay, and then part B. Part B, I now have to interpret what this means. Question, yes?
What about when u is equal to 0, 0?
Okay, so u cannot equal 0, 0, because u has to be a unit vector. So you can come up with some crazy u vectors, but they have to fit that constraint, I suppose, that u has to be a unit vector. Okay, now I'm glad you think about that, because then that a squared plus b squared that we encountered, there would have been a hidden division by 0 in there. But it can't happen because u has to be a unit vector. Cool. All right, use the directional derivative to find the direction of the tangent line at 0, 0 to the curve of intersection of f and y equals x. Okay, so basically, whatever our surface looks like, sure. I'm just going to draw. I don't know what the surface looks like. I'm not going to try and figure out what it looks like, but here's the line y equals x. If we take the plane y equals x and we take that y equals x, that isn't equals, doesn't look a lot like it, does it? Let me replace that. if I take this y equals x down there, and that's interesting. I think the focus of the projectors has been changed slightly over the weekend. Anyway, y equals x. No. Oh, it's this one not fully down. That's what it is. All right. Why not? Let's put it down. Let's have a look. That's the right one. That's the. See how the knob? There's no knob for the left one. Gosh. World-class university. Here we go. Well, I can attest to that because I studied for a semester at Berkeley, which really is world-class, and they've got knobs falling off and stuff as well. So y equals x. So if we take that line y equals x and we turn it into a plane, so the plane y equals x, it'll slice through our surface and leave some sort of curve of intersection, and who knows what the curve of intersection looks like? Something like this. Okay, so there's my curve of intersection if I slice through my surface. And so what I'm wanting to do, let me draw a tangent line now. I'm just changing color slightly. Here we go. So here's our tangent line. And I'm wanting to get the direction vector. So there, I've just tried to draw an arrow along there. There's an arrow. So I'm trying to get that arrow. I'm trying to get the direction vector along the tangent line. Now that direction vector has a shadow, if you will, down on the xy plane. I'm drawing a sort of shadow arrow. And it's that projection down onto the xy plane that is my u. Okay. Because u's only a two-dimensional vector, remember? U's just got an a and a b, and it's a two-dimensional vector. If you want to draw it as a little arrow, you'll draw it on the xy plane. Okay? So basically, if you're standing on the surface, you're a little ant on the surface, down there at the origin, and you want to walk in the direction of y equals x, what you'd be doing is you'd be walking along that curve. You'd be walking along that C curve. So let's have a look. What is u? U is a direction vector along the line y equals x. There are infinitely many vectors along the line y equals x, and they are all characterized by having their x and y coordinates equal. To turn it into a unit vector, you'd have to divide by the magnitude. So that vector that I've got at the top there, I've chosen to use 1, 1, because to me it's the simplest, but you could use 2, 2, or 10, 10, or 1,000, 1,000, or pi, pi. But basically the x and the y have to be the same because that's what characterizes all vectors that are pointing along the line y equals x. But then whatever you choose to put in your numerator, it's going to have a corresponding denominator of the magnitude of whatever's at the top. Okay, so that's my u. All right, let's work out what du is. Now we can work that out from first principles, but we don't have to because we've already got that result that's at the very top of the screen over there. And we know that our slope is going to be a squared b given any specific a, b. So it's going to be a squared b, which is 1 over 2 root 2. Okay, fine. That's nice. But how's that going to help us find what we really want, which is that black arrow that's going along the tangent line? Good grief, I've got terrible handwriting. Oh well, everybody has their flaws. That's one of mine. Got to embrace your flaws. So how do we interpret that? So here is where it becomes important that u is a unit vector. Back probably on Friday, Thursday sometime, I said it's important that u is a unit vector, and I'll tell you why at some point. And this is now, okay? Because we get back to that thing that we've had before, which is that if I have a delta z, and here I have a delta, well, I can't call it delta x, I can't call it delta y, let me just call it delta xy, then this slope is equal to delta z over delta xy, and by xy I mean something on the xy plane, it's something on the ground that's changing, okay? Now the slope is my directional derivative, and that tangent direction u. So what I'm trying to draw there, what I'm trying to draw in this black picture over here, is basically what's going on with the black stuff in that picture over there. I've got my direction vector is actually along my tangent line, and its projection onto the xy plane is a vector along that line y equals x. If I fix my the projection onto the xy plane to be u, then I know that the magnitude of that projection onto the xy plane is just 1. Okay? So I know what my directional derivative is. It's that number over there, that 1 over 2 root 2. And I know the magnitude of my, if you think of a slope as being, what is it, rise over run, or vertical over horizontal, however you think about it, the magnitude of the horizontal is 1. So therefore, my magnitude of my slope is simply the magnitude of the vertical. It's the change. It's the change in z. So basically, the magnitude of my change in z is equal to du. Could be going down. So I should be careful here with using those absolute value signs. Yes, in fact, I'm going to delete that because the absolute value signs are not actually perfectly correct there. There was a question? I heard my name? I'm not seeing a hand? Okay, cool. So basically, I know this is 1. This is the mystery that I want to solve. This is 1, the slope is 1 over 2 root 2. So something over 1 gives me 1 over 2 root 2. Well, then the something must be 1 over 2 root 2. So my delta z is 1 over 2 root 2. So I was kind of belaboring all of that, but what it basically comes down to is direction of tangent line is my u, give me my x and y coordinates. What were they? 1 over root 2. 1 over root 2. And my z coordinates at my delta z, and my delta z is going to be 1 over 2 root 2. Because my direction of motion down in the xy plane is defined as a unit vector, it means that whatever I get as my directional derivative, I can simply take without any further work as my change in z. Because slope and change in z will be the same in magnitude because it's vertical over horizontal, and horizontal has been fixed at 1. So it's important, I need to say the sentence correctly. Because the definition of directional derivatives demands that your direction is framed as a unit vector, it means that your directional derivative, which is a slope, can be interpreted as a change in z, and hence as the z component of a direction vector. I hope that is clear. Because that's what a direction vector is. A direction vector says, I'm over here, but I want to go in that direction. In other words, I've got an x, y, and z, but I want to change them. So how am I going to change them? So your direction vector is your change vector. It says, here's where I am, but I want to change my x, I want to change my y, and I want to change my z. So that's what a direction vector is. It's all about change. So if we change our x by 1 over root 2, and we change our y by 1 over root 2, and we figure out what slope that results in, that slope is then our change in z. Question?
For the last line, isn't 1 over root 2 a over the unit vector, not just a?
Hello, stylus. You were doing something very odd there. Don't you dare crash on me. Don't you dare crash on me. Last semester the software crashed. Oh, crikey. Let's minimize it and let it have a moment. Are we still being crazy? Yes, we are still being crazy. Oh, crikey. This happens occasionally. It happens occasionally. I don't really know why. I'm opening another one and we'll just move on. But basically, okay, now it's jumped away. Give me a new one. We had our u equals 1 over root 2. In other words, 1 over root 2, 1 over root 2. And that's our AB. Okay. So our A is 1 over root 2 and our B is 1 over root 2. And let's just see if it's still being crazy over document 1. Yes, it's still being crazy over document 1. It'll all be fine. Everything will be fine. It'll be fine. So that was the end, really. That was the end. I'd finished exercise 112. So at some point when the software is all calmed down, I'll go and sort out that document. But for now, you try 113.